What is up, you guys? So in this lecture, we're going to answer a question. Does the Markowitz Portfolio Optimization always work? That's it. And while you're here, consider subscribing to the channel if you want to see more on portfolio theory, stock market analysis, and more of those good stuff. So without further ado, let's get started. Now, I've decided to call this lecture, Does Markowitz Always Work? Because that's what it is. We're going to see why Markowitz portfolio optimization problem fails in some scenarios. Why does it give inefficient results? What's going on? Now, before we get into the math of the Markowitz portfolio optimization problem, I'm on Google Colab right now and I'm going to show you a small test case where Markowitz fails to give good results. So first I'm going to import some packages such as NumPy and matplotlib's pyplot, and for the sake of presentation I'm going to set a random seed to 2, and we're going to create along the way some fictitious stocks. So let's say I'm observing a 100-day window and I've got two stocks. The first one is an increasing stock. It's doing really well. Every day it increases by, I don't know, let's say $1. Or let's say $0.1 as such. There you go. So if I want to plot this stock, it will look something like this. There you go, just a stupid straight line. Really, it's just a fictitious stock. And another stock which is dependent on X1, but this time we're going to add some Gaussian noise with zero mean and let's say 0.001 variance, and we're going to take T samples. There you go. And right here I'll plot X2 on top. So there you go. X2 is X1 with some, 0.001 variations. Read it. Okay, so let's say I've got those two stocks, fictitious as they are. Let's insert both in a matrix X as such, and let's compute the mean of the prices. So we go mu, which is mp.mean of x, set the axis to 1, and let's take a look at mu. It's just a 2 by 1 vector. The first entry is the mean of x1 and the second one is the mean of x2. So let's also compute the sigma, the covariance matrix, that is the expectation over x transpose x, or x transpose in my case, minus mu times mu transpose. Let's take a look at sigma. Actually, that's not the right way to do it, because the equation right here is the expectation x transpose minus mu transpose. But this guy performs an inner product, so this guy is a scalar. However, we need mu transpose, so the proper way to do that is using NumPy's outer, that is outer product. So it takes mu transpose. So I'm going to replace this over here, and this is my correct sigma. So I'm going to stop right here because we need to rederive some the solution of the Markowitz portfolio optimization problem for a simplified case. Just for the sake of presentation, I'm going to take a simplified Markowitz portfolio optimization problem. That is, I'm going to minimize my risk, that is W transpose sigma W, subject to, and I'm going to put a strict constraint, and only one constraint, just for the sake of presentation. And this is one valid, variation of the Markowitz portfolio optimization problem. It's when you say W transpose mu is R min. If you recall, in my previous lectures on Markowitz portfolio optimization problem, we had some additional constraints, such as the sum of Wi is 1 and each Wi is positive. But we're going to drop those two constraints just to get a simplified solution. So the Lagrangian right here is a function of W and, let's say, a Lagrangian multiplier, let's say alpha. that is my cost W transpose sigma W minus alpha the constraint, that is W transpose mu minus R min. Now setting the derivative with respect to W to 0, what we're going to get is the following. So we're going to derive the Lagrangian as such. So I'm only replacing the Lagrangian. Now the derivative of the first term, since sigma is symmetric, we get 2 sigma W minus, now the derivative goes over here. Actually, let's put this as a plus and absorb the minus inside. We get a minus alpha W transpose mu plus alpha R min equal to 0, right? And now performing the partial derivatives on the second term, this guy goes to 0 because it's independent of W, whereas the first guy gives us a minus alpha mu, that is 0, okay? So what we get is simply 2 sigma W, which is alpha mu. Over here we get a sigma W, that is alpha over 2 mu. Inverting sigma, we get W, that is alpha over 2 sigma inverse mu, right? Now we need to compute alpha. Well, the way you can do that is replacing your W right over here so that you get, that is, we're going to solve for alpha such that my constraint is satisfied. So such that W transpose mu is R min. So replacing W, the one we got over here, right? Replacing that guy over here, we get alpha over 2 sigma inverse mu all transpose mu is R min. That gives us alpha over 2 mu transpose sigma inverse mu is R min. Notice that over here we use the fact that sigma inverse transpose is sigma transpose inverse, but sigma transpose is sigma, so we get sigma inverse. Okay? Again, sigma transpose is sigma because sigma is symmetric. Okay, now let's compute alpha. We get alpha is multiplying by 2 on both sides and dividing by this whole term right here. We get 2 R min over mu transpose sigma inverse mu. Okay? Replacing this alpha right here, let's call it alpha star because it's the optimal Lagrangian multiplier right here, so that we get the optimal weight vector. Finally, we get that the Markowitz optimal weight vector is 2R min over, don't forget the 2, which is right here, multiplied by mu transpose sigma inverse mu multiplied by what's rest, that is sigma inverse mu. The 2 and the 2 cancel, and finally we get that the optimal weight vector is R min, the minimum accepted returns, over mu transpose sigma inverse mu multiplied by sigma inverse mu. That is what Markowitz tells us to do. So Markowitz tells us that if you have your sigma inverse, you have your mu and the R min, you can go ahead and, using this equation, get your optimal weight vector. So if we go back to Google Colab and we want to implement this equation, well, we need to compute the inverse of sigma, that is sigma inverse using NP linear algebra dot inverse sigma. So we need sigma inverse mu and mu transpose sigma inverse mu. So let's start by sigma inverse mu. So sigma inverse mu is np.mat_mul sigma inverse mu, okay, and mu transpose sigma inverse mu is np.matmul mu transpose times sigma inverse mu. Okay, now I can compute my W, that is R min, so R min over mu transpose sigma inverse mu times sigma inverse mu as such, and just print it, and there you go. So I just want to pause over here and let you wonder. This is not, neither it is intuitive nor is it logical, because what Markowitz over here is telling us to do is allocate $81.93 in X1, that is the increasing line, and minus $81.73, that is hold a short-term position in asset 2. In other words, money is borrowed for this particular asset. This doesn't make sense because, X2 is almost the same as X1. Actually, if I go ahead and do this, X2 is X1, look what happens. Let's run everything again. It's telling you to put 0.125 in asset 2 and 0.075 in asset 1. A minor change in the variance led to very different results. Notice that a variance of 0.001 on an increasing stock is almost nothing. So very small changes led to very different results. Actually, let's go ahead and do matmul to make sure there's a return of 1. W times mu, and it's 1, yes. But what I mean to say is, if I go ahead and remove this, again, diverging results. So from a small change in X2, we were at short position to a long position, which doesn't make much sense. So the question here is, what's going on? Well, the answer lies, surprisingly, in the eigenvalues of sigma. So if I go ahead and show you the eigenvalues, np.linearalgebra dot, I think it's eigen, of sigma, there you go. So those are the eigenvalues and those are the eigenvectors. Well, I'm only concerned with the eigenvalues, and there you go. A very large eigenvalue compared to a very small, if not zero, eigenvalue. So a measure over here is the condition number of sigma. So if I go ahead and, divide the largest, so if I think we can get the largest by max, yes, and divided by the minimum. So the maximum eigenvalue divided by the minimum eigenvalue gives you a very large number. And in linear algebra, this is known to give unstable results. Statistically speaking, when there is some degree of collinearity between the returns of your assets, the matrix sigma will give you a very large condition number. So the higher the collinearity is between any two assets, here is a very small example. Let's say your matrix scales to, 100 assets, and pick just 2 assets that are collinear or highly collinear, then your condition number is going to be large. And even more, if you want to be mathematically rigorous, you're computing the inverse of such an ill-conditioned matrix. So while inverting this matrix, when a small eigenvalue is inverted, then you're going to diverge. Some numbers are going to be really large when scaling, when multiplying your mu with your sigma inverse, and hence your W is not going to give logical results, okay? What we would love to see over here is, since both stocks are behaving almost the same, then intuition suggests that we should allocate the same amount of money in both stocks, right? Not a long position in one stock and a short position in another stock. It doesn't make much sense, right? and in the extreme case 0.125 and 0.75, as we saw. It doesn't make sense. So this problem has been addressed in the past, and so for large matrices, this is sometimes referred to as the 1 over n puzzle. So people such as Di Miguel, Victor Di Miguel, Lorenzo Garlapi, and Raman Upal have actually addressed this problem, and it's in the paper entitled Optimal versus Naive Diversification. How inefficient is the 1 over n portfolio strategy? So naive diversification is when you allocate the same amount of money in each stock. So 1 over n refers to if you have n stocks and $1, I'm going to allocate 1 over n in every stock. They show that when your matrix scales really large, you can actually do good with this naive strategy. Now, this is a surprising result. It's not really intuitive. It could be intuitive when we have high collinearity between assets. So as we saw with the two fictitious stocks, yes, 1 over n strategy is really good, and could be argued to be optimal. However, other people have looked at this problem in a different way. For example, Joshua Brody, Ingrid Dobishis, Christine DeMol, Domenico Giannone, and Loris have looked at this problem in a different way. Those guys actually said, you know what? Let's view the Markowitz Portfolio Optimization problem as an inverse type problem. That is, we're going to regularize the variance by some term. Mathematically, this is not a new remedy. In regression type problems in machine learning and data science, you might have seen this concept term ridge regression. This is similar to, but it's not the same as, ridge regression. And in signal processing, this is seen as regularization of your ill-conditioned matrix sigma. So what these guys propose is say, you know what? We're going to take the same problem that Markowitz addressed, mean variance problem. We're going to take it, but instead of minimizing as is, we're going to add a term right here that is a quadratic penalty. That is, we're going to add a scalar multiple of the L2 Frobenius norm of the weight vector. Okay? And we're going to minimize over the weight vector as Markowitz did. And we're going to take the same constraint, that is the minimum return constraint. That's it. So this goes back to what is called Tikhonov regularization, named after mathematician Andrei Tikhonov, where he was studying inverse problems, and which is applied today in machine learning and statistics, which is sometimes referred to as ridge regression. Now, such a penalty can be added to regularize any quadratic program. So what's going on here? So we're not going to solve this problem. Actually, we have the solution. This problem is actually, if you rewrite the same exact problem, so we're minimizing, nothing has changed, right? W, the L2 norm on W is actually W transpose W, right? Subject to the same exact constraint. Nothing has changed. Now, the cost, if we factor W transpose on the left-hand side and W on the right-hand side, so if I go ahead and do this and this, we get a sigma plus lambda I, subject to the same exact constraint. Nothing has changed. Now, how cool is that? This is a Markowitz type optimization problem. It's the same exact thing. Nothing has changed except for one thing, the covariance matrix, which is causing us the problem, right? It's the matrix that is ill-conditioned. So look what happened over here. This guy is now regularized. Call it sigma prime. So sigma prime, so if I go ahead and, write sigma prime instead of sigma as such, we get the same problem, but with sigma prime instead of sigma. What does that mean? It means my solution is there. What is it? It's right here, but with sigma prime instead of sigma. As simple as that. So my W star, let's call it, bridge, because this is a bridge type problem, is I'm going to copy paste this guy, same exact thing, but only replacing sigma prime, that is sigma plus lambda I inverse mu, multiplied by sigma prime inverse, that is sigma plus lambda I inverse, multiplied by mu. Okay? This is your new regularized solution. This is what Brody and his friends suggest to, cure or remedy an ill-conditioned type Markowitz optimization problem. So, informally speaking, we have diagonally loaded our sigma. We have added a multiple of lambda on the diagonal entries of sigma. Well, what does that have an effect on the eigenvalues? What does that have an effect on the condition number? Well, if I take a look at the condition number of sigma prime now, it is, well, let's define sigma first. It's, sigma max over sigma min, where sigma max is the maximum eigenvalue of sigma and sigma min is the smallest eigenvalue of sigma. Well, if you go ahead and take a look at the condition number, which is referred to in the literature as kappa, and could have many other definitions. You can find a more, topological definition of condition number where, it's the norm of lambda in a unit, something like that. But in numerical linear algebra, you could also find this definition right here. It is going to be, what is the largest eigenvalue of sigma plus lambda I? It is sigma max plus lambda over sigma over, what is the smallest eigenvalue? It's sigma min over lambda. All your eigenvalues have been pushed by an amount of lambda, okay? Now you can actually prove that this condition number will do much better than this one. It's obvious. When sigma min is very small, actually in the extreme case when it's 0, this guy explodes, whereas this guy remains numerically stable as a function of lambda. So this is what, Joshua Brody and his guys suggested, along with another one that is the sparse regularizer, but this is for sparse portfolios. We'll be talking about that in future lectures, but now let's focus on the L2 regularization. Okay, and now let's see if this actually, helps us in our small fictitious test case. So if I go back to my Google Colab notebook, and right over here, I, instead of inverting sigma, I'm going to add a lambda times NP identity 2 because I have 2 stocks. And lambda is reserved for lambda expressions, so I'm going to be using lam as such. So my lam, let's fix it, I don't know, let's put something, you can actually study the effect of lambda on the returns. Let's fix it, I don't know, to 20. Let's run this. And there you go, equal allocation. So a 1 over n naive allocation is optimal in a ridge sense where your lambda is 20. Let's change this to 10. There you go, 0.1 as well. 1, also 0.1. Let's put it 100 or 10,000. There you go. Each weight is converging equally. So they're both converging towards 0.1. So yeah, that's it. That's all I have to say in this lecture. Before going ahead, so the moral of the story over here is that Markowitz is a very elegant solution to the portfolio theory, and you need to go ahead and do some analysis before you go ahead and apply it blindly to your stock market analysis. Because I've been receiving many emails after my Markowitz Portfolio Optimization lecture, and there's many people asking me, well, I'm using 1,000 stocks, so that's wrong to do. You grab 1,000 stocks blindly and you just, apply this simple equation, which is right here. No, that's not the proper way of doing it. The proper way is to study collinearity before, study how good of a, how well conditioned your matrix is. Is it well conditioned yet? If it's relatively well conditioned, just, you can try to compute your W and see how things go. And if not, why is it now well conditioned? Does there exist any collinearity between any two assets or more that leads to unreasonable or illogical results? If so, let's try to regularize as we did right here. And let's see if things go well from there. Just to keep in mind as well that this is only one way of solving this type of problem. Indeed, there exists a lot of different, remedies to tackle this ill-conditioned problem. Another one being a very elegant one that I'm not going to be talking about in this lecture, but I will keep it to future ones. And it's really related to the concept of principal component analysis or reduced rank optimization. It's where, you grab your sigma and you remove the components that yield in low eigenvalues so that, your eigenvalue is well conditioned. I'll be talking about that in future lectures if I receive emails or comments related to this particular concept, but keep in mind that there's a lot of other. So by cutting out those small eigenvalues, this is usually referred to as the truncated singular value decomposition. It's where you, perform an eigenvalue or singular value decomposition and you remove, the small eigenvalues. So you truncate your singular values of your matrix. And I'm not going to be talking about this in this lecture. It's going to be addressed in future lectures if I see a lot of comments and emails asking me to, conduct this lecture. So thanks for watching. I hope you found this lecture beneficial. If you did, please leave a like on the video, subscribe to the channel. If you have any questions whatsoever, kindly leave a comment down in the comment section below and I'll make sure I'll get to it as soon as possible. And if possible, kindly donate to my Patreon account any amount you wish. Thanks for watching and I'll see you in future lectures.